lecture we see exercise number 1.3, question number 4 and question number 5. So our question 1 to question 5 we see in question 5. Now we see next example, that is question number 5. If y is equal to x raised to y is equal to e raised to x minus y, then x raised to y is equal to e raised to x minus y, then show that dy upon dx is equal to log x divided by 1 plus log x bracket square. If we have given this, so see x raised to y is equal to e raised to x minus y, which is in the form of function raised to function. So here we take logarithm on both sides. Take logarithm on both sides. Therefore, log x raised to y is equal to log of e raised to x minus y. Then y log x is equal to x minus y into log e. Y log x is equal to x minus y and value of log e is 1. Therefore, write y log x as it is. This minus y here in this side it becomes plus y is equal to x. Now we take y common from this. Y into 1 plus log x is equal to x. Therefore, y is equal to x upon 1 plus log x. Now differentiate with respect to x using quotient rule. That is dy upon dx is equal to phi into v is what 1 plus log x into take a derivative of x, that is 1 minus x into derivative of 1 plus log x. Derivative of 1 is 0 and derivative of log x is 1 upon x divided by v square means now 1 plus log x into 1, that is 1 plus log x minus x into 1 upon x. So x will get cancelled, minus 1 upon 1 plus log x whole bracket square. 1 minus 1 will get cancelled here. Therefore, dy upon dx is equal to log x upon 1 plus log x bracket square. Hence, it is proved. Now see next question, question number 7. These are very important questions. Y is equal to, if y is equal to root cos x plus root cos x plus cos x plus and so on up to infinity, then show that dy upon dx is equal to sin x divided by 2y minus 1. Very important question. This is of the type y is equal to under root f of x plus f of x plus f of x plus and so on up to infinity. Then the answer of this type of function is dy upon dx is equal to f dash of x divided by 2y minus 1. Remember that? Answer of this type of question, under root f of x plus root f of x plus and so on up to infinity, then answer of this type of questions is dy by dx f dash of x divided by 2y minus 1. So see our example, y is equal to under root cos x plus, now look at this is again y which starts from cos x plus cos x or up to infinity. So we see, consider this function as again y, because this is the value of y, root cos x plus root cos x up to infinity. So here I am writing the cos x as it is plus The next function, remaining part of function, we say it is again y. Now, for the square root, we take square on both sides. Therefore, y square is equal to the square root will cancel cos x plus y. Y square is equal to taking square on both sides. Now, differentiate with respect to x. Derivative of y square to y, derivative of y dy by dx is equal to derivative of cos is minus sin x plus derivative of y dy upon dx. Therefore, take the terms which are multiplied by dy by dx in another side is equal to minus x. Therefore, now take dy by dx common from this is equal to into 2y minus 1 is equal to minus sin x. Therefore, dy upon dx is equal to minus sin x divided by 2y minus 1. Yeah, 1 minus 2, I will have to prove that. So, if I am taking minus common from the denominator, then 1 minus 2y. So, minus minus will get cancelled. Sin x upon 1 minus 2y. But always remember that if y is equal to, for CT and examples, this type of questions are very important. Then what is the answer? Is equal to derivative of this function divided by 2y minus 1. Any function, if there is root tan x plus and so on, the answer of this type of question is dy upon dx is equal to derivative of tan sec square x upon 2y minus 1. Same, only you have to take the derivative of the function in numerator and the denominator is fixed in this type of function. Now see next one. Example number 8. Again, you should try to solve the examples. Now here, instead of the f of x, we have given log x. Then what is the derivative of log x? That is 1 upon x. So derivative 1 upon x and the remaining part of 2y minus 1. So you should try to solve the next example, question number 8. Now see next question number 9. Y is equal to x raised to and so on up to infinity. Now this is in the form of y is equal to function raised to function and so on up to infinity. Then show that dy upon dx is equal to y square upon x into 1 minus log y. So look at here, y is equal to x raised to x. Again write the x as it is, and this is again our y. That is y is equal to x raised to y. Now taking log on both sides, because this is a function raised to function. So taking log on both sides, then log y is equal to y log x. Now differentiate with respect to x. Derivative of log y 1 upon y into dy upon dx is equal to product rule y into derivative of log x is plus 1 upon x, and log x into derivative of y is dy upon dx. Now take the terms which are multiplied by dy by dx in RHS and take dy by dx common from this. So 1 upon y minus this log y, log x is equal to 1 upon x right as it is. Now simplify this bracket. Therefore, dy upon dx into, in bracket, 1 into 1, that is 1, minus y log x divided by y is equal to y upon x as it is. Therefore, dy upon dx is equal to, write y upon x as it is, into y upon 1 minus y log x Therefore y into 1 y square in bracket x into 1 minus y log x. X into 1 minus log y, and here derivative of log y is equal to y into log x. So this is our answer. Y square is equal to 1 upon x into 1 minus log y. Now see next example, that is e raised to y is equal to y raised to x. Y into derivative plus log x into derivative of y, that is dy upon dx. Next example, last one, e raised to y is equal to y raised to x. Then dy upon dx is equal to log y square divided by log y minus 1. Now see, again we take log on both sides. On both sides. Therefore, log e raised to y is equal to log of y raised to x. That is y into log e is equal to x into log y. But value of log e is 1. So, y is equal to x into log y. Since log e is equal to 1. Therefore, differentiate with respect to x. X as it is, derivative of log y 1 upon y into derivative of y dy upon dx plus log y as it is into derivative of x is 1. Therefore, dy upon dx into minus x upon 1 into dy upon dx is equal to log y. Now take dy by dx common. In bracket 1 minus x upon y is equal to log y. Now simplify this. Therefore, dy upon dx in bracket 1 into y minus x divided by y is equal to log y. Therefore, dy upon dx is equal to log y into y upon y minus x. That is y into log y upon y minus x. And here we have to prove. What we have to prove? That is log y whole bracket square divided by log y minus 1. If here we use log y minus 1, so this is y is equal to x into log 1. Then value of y is instead of this, if we write y into log y, value of y is x into log y and the log y as it is upon, again I am writing value of y is x into log y minus x right as it is. So look at here, x into log y square, and if I am taking the x common from this, then in bracket we will get log y minus 1, x will get cancelled here. So answer is log y bracket square upon log y minus 1. Here instead of 1 we use this, so say and write here from equation 1. Here we use the value of y, that is y is equal to x into log y instead of y, and then the x will get cancelled here, log y, so log y bracket square upon log y minus 1. Hence it is proved. Here we finish our next exercise, that is exercise number 1.3. Now we start our next new point, that is derivatives of a parametric functions. So we see first theorem for derivatives of, as like we see the theorem of composite function, then next we see inverse function theorem. Similarly, we have to prove the derivatives of parametric function. In exam, we have to ask the theorem for 4 marks or 3 marks. Prove the example or prove derivatives of composite function theorem, inverse function theorem and parametric function theorem. In this chapter, the 3 theorems are very important. The last theorem in chapter we see, that is derivatives of parametric functions. First we see theorem, which is very important. Derivatives of parametric functions. So first write a statement. What is statement? If x is equal to f of t and y is equal to g of t are differentiable functions of parameter t. If x is equal to f of t and y is equal to g of t are differentiable functions of a parameter t, then y is a differentiable function of x parameter t such that y is a differentiable function of x, then and dy upon dx is equal to dy upon dt divided by dx upon dt, but first the denominator must be non-zero. Now we see the proof of our theorem. First we see increments, which are the 3 theorems are similar. So first we take, let delta x be the smallest increment in x. Delta x be the smallest increment in x. Also, delta y and delta t be the corresponding increments. In y and t respectively, means increment of y is delta y, increment of t is delta t. Now look at here, as delta x tends to 0, delta y tends to 0 and delta t tends to 0, because look at here, x is a function of t, y is a function of t, means as x tends to 0, y tends to 0, then the obviously delta t tends to 0, because our x and y both are the functions of t. So if xy becomes 0, then t also becomes 0. Now consider an incremental ratio. Consider an incremental ratio. That is delta y upon delta x is equal to delta y upon delta t divided by delta x upon delta t. Now here we are taking limit as a delta t tends to 0 on both sides, because our functions is in the form of t. So taking limit as a delta t tends to 0 on both sides. Therefore, limit delta t tends to 0, delta y upon delta x is equal to t tends to 0, delta y upon delta t divided by delta x upon delta t. So now separate the limits. Therefore, limit, now see here, we know that if delta x tends to 0, then delta t also tends to 0. So instead of the delta t tends to 0, I am writing here delta x tends to 0, delta x tends to 0, delta y upon delta x is equal to, now separate the limit of RHS. Limit delta t tends to 0, delta y 0 delta x upon delta t. Say equation number 1. Now look at here, what we have given that x and y are a differentiable functions of t. So their limit, that is dx upon dt and dy upon dt exists. So right here, since x and y are differentiable functions of a parameter t, then the limit is exist. Then their limits are exist. That is, limit delta t tends to 0, delta x upon delta t is equal to dx upon dt, and limit delta t tends to 0, delta y upon delta t is equal to dy upon dt. So our equation 1 becomes, therefore equation 1 becomes limit delta x tends to 0, here RHS of equation 1 becomes is equal to dy upon dx divided by dy upon dt upon dx upon dt. Now here, if RHS of equation 1 exists, so LHS of equation 1 also exists, as RHS of 1 exists and it is finite, therefore LHS also exists. LHS also exists. That is, limit delta x tends to 0, delta y upon delta x is equal to what? Dy upon dx. Therefore, equation 1 becomes what is LHS? Dy upon dx is equal to dy upon dt divided by dx upon dt. Hence, it is proved. This is called as a derivatives of parametric functions. In exam, we have to ask the theorem for 3 marks or 4 marks. Prove the theorem or prove the following result. That is, we have given the statement and we have to give its proof. The 3 theorems are most important in our chapter differentiation. Composite function, inverse function, and the next one is parametric function. Now we see examples of parametric functions. Suppose for example, dy upon dx is equal to and dy upon dx, if x is equal to a t raised to 4 and y is equal to a t square, a t raised to 4 and y is equal to 2a square. Then find the dy upon dx. This is an implicit function. Both x and y are functions of parameter. T bar t is a parameter here. So the solution, x is equal to a t raised to 4 and y is equal to 2a square. Now x and y both are the functions of parameter t. And we see in last lecture, if y is a function of x, then we differentiate with respect to x. Similarly, here x and y both are the functions of parameters t. So we differentiate simultaneously. Differentiate with respect to parameter t. Take simultaneous derivative. So what is derivative of x? Dx upon dt. Here a is constant right here. Now what is derivative of t raised to 4? What is derivative of x raised to 4? 4x cube. Similarly, derivative of t raised to 4 is 4t cube. So here 4at cube. Now y is equal to 2at square. Then derivative dy upon dt. 2a is constant. Derivative of t square is 2t. So which is equal to 2 into 2, 4at. Now here we get value of dx upon dt and dy upon dt, and we have to find dy upon dx. So here we are using this theorem, parametric function theorem. Therefore by using parametric function theorem, d1 upon dx is equal to d1 upon dt divided by dx upon dt. And what is value of d1 upon dt? 480. And dx upon dt? 480 cube. So 4a will cancel, and t upon t cube. That means here 1 upon t square. Therefore dy upon dx is equal to 1 upon t square. And in next lecture we see our next exercise, that is exercise number 1.2.